Welcome back. In this session, we'll explore one of the most exciting problems in generative AI, text-to-image generation, the ability to take a natural language description and turn it into a realistic, high-quality image. This technology powers some of today's most widely used AI tools, from DALL and Stable Diffusion to MidJourney and Imagen, and it's transforming fields like art, design, marketing, entertainment, and education. But building such a system is extremely challenging. The model has to bridge two very different modalities: natural language understanding on one side and high-fidelity image synthesis on the other. It must capture not only the meaning of the text, but also translate that meaning into visual details, textures, spatial layouts, and stylistic elements. In this video, we'll start by clarifying the key requirements for a text-to-image system, then frame it as a machine learning task. We'll compare two main families of approaches: autoregressive models like DALL and Muse, and diffusion models like Imagen and Stable Diffusion, and see how they work under the hood. From there, we'll walk through data preparation at scale, model development and training, sampling strategies, and the practical challenges of efficiency, speed, and cost. Finally, we'll put everything together into a full system design pipeline, from data to training, optimization, inference, and safety. By the end, you'll understand how modern AI systems are able to generate stunning, diverse, and realistic images directly from text prompts. The problem is to design a system to generate realistic images from a piece of text. Here are some good requirements to ask: what resolution do we want? How much training data do we have? What's the latency requirement? How complex can the text prompt be? Is there a domain or type of images we are focusing on? Our objective is to design a system that takes a user's text prompt and outputs a high-quality image that faithfully matches that description. This is inherently a multimodal learning problem, bridging natural language understanding and high-fidelity image synthesis. The mapping between text and image is many-to-many. A single prompt can yield many plausible images, and different prompts can yield overlapping visual concepts. So the model must capture rich semantic alignment. 1. Autoregressive models. DALL, Muse. Autoregressive methods frame generation as next token prediction, much like in language models, but with a combined vocabulary of text tokens and visual tokens. Pipeline. Text tokenization. The prompt is tokenized into a sequence of discrete tokens using a subword tokenizer, e.g., BPE. Sequence modeling. A decoder-only transformer predicts the next token in the sequence, starting with text tokens and then generating image tokens one by one. Image reconstruction. The image tokenizer, e.g., VQVAE or VQGAN, converts the discrete visual tokens into the final image. Advantages: strong compositionality. It can generate images with multiple objects in correct spatial relationships. Challenges: computational cost scales linearly with sequence length, making high-res images expensive to generate. Errors can accumulate since generation is strictly sequential. Notable example: DALL-E's ability to generate surreal but semantically coherent images, e.g., an armchair in the shape of an avocado. 2. Diffusion models. Imagen 3, DALL, 2. Stable diffusion. Diffusion approaches model image generation as a gradual denoising process. They learn to reverse a forward process where Gaussian noise is progressively added to an image. Pipeline. Text encoding. A large language model or a clip text encoder embeds the prompt into a dense vector space. Noise-to-image generation. Starting from pure noise, the model iteratively predicts and removes noise conditioned on the text embedding. Guidance mechanisms. Classifier-free guidance boosts alignment with the prompt without requiring extra classifiers. Advantages: produces highly detailed, realistic textures, e.g., skin, clouds, glass reflections. Flexible trade-off between quality and speed by adjusting the number of denoising steps. Challenges: requires many forward passes during inference, which can be slow without acceleration, e.g., distillation, latent diffusion. Notable example, Imagen 3's ability to produce photorealistic faces and complex scenes with minimal artifacts. In our text-to-image generation system, data preparation is absolutely critical because the quality of the model will be directly determined by the quality and relevance of our training data. We start with a massive dataset, 500 million image caption pairs, which offers a rich foundation but also demands careful curation. On the image preparation side, we first filter out inappropriate or NSFW content to ensure safety and compliance, especially if our model is going to be used in a public or commercial context. We also normalize images, adjusting their size, aspect ratio, and color space, so the model receives a consistent input format, which makes training more stable and efficient. For caption preparation, we address common data quality issues. Missing captions are either filled in through automatic caption generation tools or excluded if too unreliable. We enhance captions by improving grammar, clarity, and descriptiveness, which helps the model better align text with visual concepts. Importantly, we remove poorly matched image caption pairs, for example, a caption saying "a red sports car" paired with an image of a blue sedan, as these can confuse the model and degrade generation quality. The goal of this stage is to create a clean, high-quality, and semantically consistent dataset, so the model learns accurate mappings between textual descriptions and visual outputs. Even a small increase in data quality here can lead to substantial improvements in generated image realism and relevance. The UNet in our text-to-image generation pipeline acts as the core denoising network in the diffusion process. Its architecture is symmetrical, with downsampling blocks on the left, a bottleneck in the center, and upsampling blocks on the right. First, downsampling blocks. Goal: extract hierarchical features and compress spatial information while keeping track of important context. Process: convolution layers, typically 3x3 kernels with padding to preserve spatial dimensions before pooling, allowing for precise spatial feature extraction. Batch normalization normalizes feature maps to stabilize and speed up training. Nonlinear activation, usually ReLU or GELU, adding nonlinearity to capture complex patterns. Cross-attention layers. At certain stages, the feature maps attend to the text embeddings from the text encoder, injecting semantic guidance early in the process. Downsampling step, often done with 2x2 max pooling or a strided convolution, having spatial resolution while doubling or increasing the number of channels. This trades fine spatial detail for richer semantic representation. Second bottleneck layer. The narrowest point of UNet with the smallest spatial resolution but the richest semantic representation. Heavy use of cross-attention here ensures that even the deepest features are conditioned on the textual description. Third, upsampling blocks. Goal: rebuild the image resolution step by step while integrating preserved spatial details from earlier layers. Process: transposed convolution, deconvolution. Increases spatial resolution by reversing the convolution process. Sometimes nearest neighbor upsampling plus convolution is used for smoother results. Batch normalization and nonlinear activation. Maintain stability and expressivity during reconstruction. Skip connections. Concatenate feature maps from the corresponding downsampling stage to recover fine details lost during pooling. This also improves gradient flow, making the network easier to train. Cross-attention, again, allows the model to reference text embeddings, keeping generation aligned with the prompt even in fine detail restoration. 4. Why UNet works well. Here, local plus. Global context. Convolutions capture local spatial coherence, while skip connections preserve fine details, and cross-attention integrates semantic context throughout. Hierarchical representation. Early layers capture edges and textures, deeper layers capture object shapes and relationships. Symmetry. Ensures that every stage of feature extraction has a matching reconstruction step, aiding in high-quality synthesis. In diffusion-based text-to-image generation, model training revolves around two complementary processes: the forward noising process and the backward denoising process. Forward process, noising process. We start with a clean, high-quality image from our dataset. Over a series of time steps, sometimes hundreds or even thousands, we progressively add Gaussian noise to the image. By the final step, the image is almost pure noise. This stage teaches the model what a fully destroyed signal looks like and establishes the distribution it must learn to reverse. Backward process, denoising process. This is the process we actually train the model for. At each time step, given a noisy image and the time step index, the model tries to predict the noise that was added. Once predicted, this noise estimate is subtracted from the noisy input, moving the image one step closer to the original. Iteratively applying this step reconstructs the original image from noise. Diffusion training workflow. Noise addition. We simulate the forward process by corrupting the original image with a known amount of noise at a random time step. Preparation of conditioning signals. For text-to-image tasks, we use a text encoder, e.g., Clip's text tower or a transformer encoder, to generate embeddings for the text prompt. Other conditioning signals like style vectors, class labels, or guidance embeddings are also prepared here. Noise prediction. The core model, e.g., a UNet or diffusion transformer, takes the noisy image, time step, and conditioning embeddings and predicts the exact noise that was added. Objective. We optimize the model so its predicted noise matches the actual added noise as closely as possible. Loss function. Typically, this is a mean-squared error, MSE, between predicted noise and true noise. Some implementations add auxiliary losses, like perceptual or adversarial losses, to encourage photorealism or style fidelity. This process is self-supervised. We don't need labeled data since the noise is artificially generated, and we always know the ground truth noise vector. By mastering the denoising process, the model can then start from pure noise and generate a completely new image guided by any given text prompt. In the sampling stage of a text-to-image diffusion model, the process begins with a completely random image, typically generated by sampling pixel values from a Gaussian distribution. This random image serves as the starting point, essentially a noisy canvas. The model then refines this image step by step. At each step, the diffusion model predicts the noise present in the current image. Using this prediction, the model makes slight adjustments to reduce the noise and gradually transform the image toward a coherent, realistic output that aligns with the text prompt. This iterative process continues for many steps until a final, high-quality image emerges. However, this process has some drawbacks. Because it relies on numerous iterative refinements, it is inherently slow, which can affect real-time usability. Additionally, the model may sometimes fail to generate images that accurately reflect the input prompt, especially in complex scenarios. To mitigate these challenges, two main techniques are commonly employed: classifier-free guidance, CFG. This method balances the influence of the conditioned model, which sees the text prompt, and the unconditioned model, which ignores the prompt. By increasing the weight of the conditioned mode, the generated images more faithfully align with the textual input. Reduction of diffusion steps. By carefully reducing the number of refinement steps, we can speed up generation without significantly compromising image quality. This technique requires tuning to maintain a balance between efficiency and fidelity. In summary, sampling in text-to-image diffusion models is an iterative denoising process starting from random noise, guided by both the learned model and the text prompt, with techniques like CFG and step reduction used to improve quality and efficiency. Diffusion models are powerful for generating high-quality images, but they face several practical challenges. 1. Resource-intensive model training. Training diffusion models requires enormous computational resources because the model must learn to denoise images across many time steps and handle very large neural networks. To address this, mixed precision training, By combining 16-bit and 32-bit floating point operations, we can reduce memory usage and accelerate training without sacrificing model accuracy. Model and data parallelism distributes computations across multiple GPUs or nodes, allowing training of larger models and larger batch sizes efficiently. Latent diffusion models. Rather than operating on full-resolution images, latent diffusion models compress the image into a lower dimensional latent space before applying the diffusion process. This dramatically reduces memory requirements and speeds up training. Second, slow image generation. Even after training, generating images is slow because diffusion models refine images step by step over hundreds or thousands of time steps. To mitigate this, parallel sampling. Some time steps can be processed in parallel or approximated to speed up generation. Model distillation. A smaller, faster student model is trained to replicate the outputs of the larger diffusion model, allowing much quicker inference. Model quantization reduces the precision of the weights and activations in the model to decrease computational cost and memory footprint during sampling, with minimal loss in output quality. Together, these strategies aim to make diffusion-based text-to-image generation more practical for real-world applications while maintaining high image quality. To ensure the quality and effectiveness of a text-to-image generation system, we evaluate the model using both offline and online metrics. Offline metrics, Inception Score, IS, uses a pre-trained image classifier, typically Inception v3, to assess image quality and diversity. High score indicates that images are both realistic and varied. Limitations, does not measure alignment with the text prompt. Fréchet Inception Distance, FID, measures the distance between the distribution of generated images and real images in a pre-trained feature space. Lower FID indicates that generated images closely resemble real-world images in terms of texture, color, and structure. Image-text alignment metrics, CLIP, CLIPSCORE, evaluates how well the generated image aligns with the input text prompt. Uses a pre-trained vision language model like CLIP to compute similarity between image embeddings and text embeddings. Ensures that the generated content is semantically consistent with the user query. Human evaluation involves crowdsourced or expert human evaluators to judge image realism, relevance, and visual quality, critical for capturing aspects of image quality that automated metrics may miss. Online metrics, click-through rate, CTR, measures user engagement with generated images in applications or interfaces. User feedback, direct input from users indicating satisfaction or issues with image quality and relevance. Conversion rate, tracks how often users perform desired actions after viewing generated images, such as purchases or content downloads. Latency, measures the time it takes to generate an image from a text prompt, critical for real-time applications. Throughput, evaluates the number of images the system can generate per unit of time, important for scalability. Average cost per user per month, helps monitor operational efficiency, especially for cloud-based or API-driven deployments. Overall, combining offline metrics with online user-centric metrics provides a comprehensive evaluation framework, balancing image quality, semantic alignment, efficiency, and user experience. This slide outlines the complete system architecture for a text-to-image generation platform, highlighting each major pipeline and service. Data pipeline. The data pipeline is responsible for preparing the training data. It cleans and normalizes images, processes and enhances captions, removes low-quality or inappropriate content, and tokenizes both text and images. This ensures that the model receives high-quality, consistent data during training, which is critical for both performance and reliability. Training pipeline. The training pipeline consumes the prepared data to train the model. This includes training the diffusion or autoregressive model to map text prompts to images. The pipeline is designed to handle large-scale datasets efficiently and may involve distributed training, mixed precision techniques, and checkpointing to manage long training runs. Evaluation pipeline. The evaluation pipeline assesses the model's performance using offline metrics like FID, inception score, and image text alignment metrics such as CLIPS-CORE. Human evaluation can also be incorporated to ensure quality, fidelity, and alignment with user expectations. This pipeline helps identify weaknesses and guides model improvements. Model optimization pipeline. After training, the model undergoes optimization to improve speed, reduce resource requirements, and maintain high-quality outputs. Techniques include model compression to shrink the model size, model distillation to transfer knowledge to smaller models, and algorithmic optimizations to accelerate inference. These steps are critical for deploying high-resolution image generation efficiently. Inference pipeline. The inference pipeline is responsible for generating images in response to user prompts. It includes multiple stages. Prompt autocomplete helps users formulate prompts quickly. Prompt safety service. A text classification model filters unsafe or inappropriate prompts. Prompt enhancement refines prompts to improve clarity, coherence, and richness of detail, improving image quality. Image generation. The core model generates images from the enhanced prompts. Harm detection ensures generated images do not contain inappropriate or harmful content. Super resolution service optionally enhances image resolution to meet high-quality standards. Overall, these pipelines work together to provide a seamless workflow from raw data to high-quality image generation, ensuring safety, efficiency, and user satisfaction.